Despite the added work over the command center, NORAD's interior protective shell was finally completed in May of 1965. The steel buildings that would eventually provide 208,000 square feet of working space took their place within the 2.5 miles of tunnels in the cavern. Now it would take 8 months just to install the complex electrical and surveillance equipment inside the mountain. The centerpiece of the new command center was an $800,000 combination camera processor projector that could display a 12 by 16-foot image of the planet in 7 colors. On that screen, commanders got a sophisticated global picture of objects they were tracking, observation posts, even satellites in orbit. The screen was fed by radar and satellite information from an array of computers around the world. By today's standards, NORAD's initial computer technology was primitive. But at the time, the massive mainframe computers were state-of-the-art. Throughout the Cold War, the computer technology race was as fierce as the nuclear arms race. Today, NORAD's Granite Sentry system remains state-of-the-art.
All the computers we use are off-the-shelf items. It's just a software that is specially designed and created to perform the missions that we require of them. Basically, we have our fingers on the pulse of Cheyenne Mountain. We can tell at a glance if there's a problem with our missile warning systems, our space defense systems, or our air defense systems throughout the mountain.
By early 1966, the power was on at Cheyenne Mountain. The sentinels at their stations. Everything waited in readiness for an event everyone hoped would never happen. After nearly 5 years of work, at a present-day replacement cost of $18 billion, the Cheyenne Mountain Complex became fully operational on April 20, 1966. The men who designed, engineered, and built the massive underground center were proud of their work. They were also quite aware of its limitations. Everyone hoped that this superstructure would never be put to the test. Even more, they prayed that it would survive that test.
The design was based on that premise. Well, the odds were rather high that you would not have a direct hit on the complex. If you had a direct hit, then the dynamic loads would be so great that the openings would collapse. There's just no way to offset the terrible stresses that would be developed in the rock.
In the end, NORAD's survival rested on a principle called circular error probability. CEP was simply the probability that a nuclear weapon, fired from halfway around the world, would fail to score a direct hit on Cheyenne Mountain.
As far as the vulnerability of NORAD, that was really mostly a function of the accuracy of the device. Because, it was a foregone conclusion that a direct hit would destroy it.
Even though it cannot survive a direct hit, the command center is designed and built to resist the effects of a nuclear weapon. Blast, heat, seismic shock, electromagnetic pulse, and radiation. The access tunnels weaken the effects of blast and heat simply by letting the blast wave pass through the tunnel unimpeded. To avoid a direct strike by the blast wave, the designers located the blast valves and blast doors at right angles to the tunnels. At the first sign of a credible nuclear threat, the blast doors are closed and Cheyenne Mountain is sealed off from the outside world. Tech Sergeant Marvin Hires and his team of specialists maintain these doors.
Here at NORAD, we have 3 blast doors. The blast doors are designed to protect the mountain from an overpressure, imploding from the inside. Each door's hydraulic system is self-contained, and the speed of the door is anywhere from 40 seconds to 15 seconds if we had to. They're perfectly balanced, 50,000-pound doors. You can actually move them with your hand.
When the doors are closed, technicians reconfigure the ventilating fans to run backwards. The reversed airflow keeps radioactive contaminants or chemical warfare agents from entering the mountain. Another engineering innovation at Cheyenne Mountain is designed to protect NORAD from the seismic shock of a nuclear blast. Massive steel springs, more than 1,300 of them, support each of the 15 buildings in the complex.
Each spring is about this big around, and the wire that makes the spring is 3 inches diameter of high-strength steel. The springs are about 1,000 pounds apiece in weight, and they stand 48 inches tall, unsprung. The weight of the buildings compress those springs to approximately 36 inches. And the purpose of the springs for all these facilities is to prevent a shock that might come through the rock resulting from either a man-made or a natural shock. These springs will attenuate that shock just as they would car springs on your